Hello. In this video, I will go over the cross product. As we discussed in the last video on the dot product, when you first learn about vectors, you learn about how to add vectors, you learn about how to subtract vectors, and you learn about how to go through and do scalar multiplication of vectors. But you don't learn definitions for how to multiply vectors. And there's two different definitions for multiplying vectors. So one is the dot product, and the other is the cross product. So to start our discussion of the cross product, we first need to go through and define vectors. So let's say that we have A1, A2, A3, and B is B1, B2, B3. And let's have a picture. So similar to our picture for the dot product, we have two vectors. Vector A and vector B. Okay, so similar to the dot product, there's actually two different definitions for the cross product. One is more theory focused, and the other one is more calculation focused, which is the same situation that we had with the dot product. So the more theory focused is given by the length of the cross product is equal to the length of A times the length of B times sine theta. And then the second definition is that the cross product can be calculated by going through and calculating the determinant of a 3x3 matrix whose components are as follows. So you have a line of ijk, and then you have a line for A and a line for B. And if you go through and calculate the determinant, you get I times A2B3 minus A3B2 minus J times A1B3 minus A3B1 plus K times A1B2 minus A2B1. So we have our two different definitions. One, this is the more theory focused of the two, and then the second one is the more calculation focused. So one thing to note that I should make clear is that the result of the cross product is a vector. The result of the cross product, the dot product was a scalar. And so it's an important difference between the two is that if you take a dot product, you end up getting a number. If you take a cross product, you end up getting a vector. The other thing about cross products that is different than dot products is that cross products are only defined for 3 dimensions. Cross products are not defined for 2 dimensions. You cannot go through and do a 2-dimensional cross product. For the most part, there's what you can do if you really want to do a 2-dimensional cross product is that you can have the third components be 0. And so that is something that we will do later on in the course when that situation arises. Okay, so the first thing, so again, this is for going through and doing calculations. And so this is for theory. So we want to go through and practice using our calculation part of the cross product to calculate a couple cross products, just to make sure that we can do that without any difficulty. So let's have a couple examples let A equal 2I minus 3J plus 4K. Let B equal negative I plus J minus K. And then if we're going to go through and calculate A cross B, it's going to equal the determinant of the 3 by 3 matrix. We'll have I, J, and K, 2, negative 3, and 4, negative 1, 1, and negative 1. So that's going to equal I times, and now you're going to multiply these two, negative 3 times negative 1, minus these two, multiply together, 4 times 1, minus J. Then you're going to multiply these two together, 2 times negative 1, minus these two together, 4 times negative 1, plus K. Now you're going to multiply these two together, 2 times 1, minus these two together, negative 3 times negative 1. Okay, and then from there we just simplify. So negative 3 times negative 1 is going to be 3 minus 4 minus J times negative 2 plus 4 plus K times 2. And then we've got a triple negative here, so minus 3. And simplify this, you get negative I minus 2J, don't forget the negative here, and then minus K. So there's one example of going through and calculating a cross product. Let's do a quick second example. Let's say A is negative 3I plus J plus K. And we'll say B is 2I plus 3J minus 4K. Then in that case, we can go through and calculate the determinant of the 3 by 3 matrix. You get IJK, negative 3, 1, 1, 2, 3, negative 4. So we end up getting I times 1 minus negative 4, which is negative 4, 1 minus 1 times 3, so minus 3, minus J, and then negative 3 times negative 4 is going to be 12 minus 1 times 2, and then plus K, and we're going to get negative 3 times 3, that's negative 9, minus 1 times 2, and so the result, if we simplify that, that's going to be equals negative 7I, and then what do we got? 12 minus 2 is 10, negative 10J, and then negative 11K. Okay, so the next thing that I want to show you is similar to what we did with the dot product. We can go through and prove that the two cross product formulas are the same. So the two definitions that we came up with for the cross product, it is possible to go from one definition to the other. And so to do that, so this is a proof. And so what we're going to do is we're going to start off with A cross B, the length of A cross B squared. All right, and in particular, the definition that what we're going to do here is we're going to start with the second definition, the calculation definition, and then prove that you can go from the calculation definition, definition 2, prove that you can go over to definition 1, the one that has the sine theta in it. Okay, so to do that, we're going to start off with this, right? So we know that the cross product, the length of the cross product, if you go through and go back, if we take this definition here and we just take the length of it, meaning that you would take the square root of the components squared, and these are the components. Okay, so you're going to take the square root of each of these squared, then you'd end up getting the following. A2b3 minus A3b2 squared plus A1b3 minus A3b1 squared plus A1b2 minus A2b1 squared. Now that's the length of the cross product, and then there's this extra square here. So we got to take that result and square it. Okay, if you do that, this square and the square root cancel, and we just get what's inside here. Okay, and then next you can go through and you can expand these. If you do that, you're going to get A2B3, each one is squared, minus 2 times A2B3, A3B2, plus A3 squared, B2 squared. So that's just this piece squared. Now we're going to square this piece. We're going to get A1B3. Each of those is squared, minus 2 times A1B3, A3B1, plus A3B1. Both are squared. And then this guy, A1 squared B2 squared, minus 2A1B2, A2B1, plus A2 squared B1 squared. Okay, and then the next step is something that you could go through and prove separately. It's not obvious just by looking at it, but we could take this and we could rewrite it into the following format. We could take this and we could have A1 squared plus A2 squared plus A3 squared times B1 squared plus B2 squared plus B3 squared minus A1B1 plus A2B2 plus A3B3 squared. Okay, now again, this is not obvious just to look at it, but you could go through and verify this. If you were to do so, you'd start here and multiply this all out and then combine it, and it would reduce into this. Okay, so the next thing, if you look at what those are, so this piece here, this is the length of A squared, right? If you recall, the length of A is going to be the square root of its components. So we have the square root of its components squared, and so we have its components squared, except there's no square root, so you just have to add a square on. So this is going to be the length of A squared. And then this is the same thing. We have the components of B squared, but there's no square root, and so it's the length of B squared. And then this, if you'll recall from the last section, this is the dot product. And so what we have is we have A dot B squared. Okay, and then next, if you go through and use the first definition for the dot product, we could rewrite this as minus the length of A, length of B, cosine theta, and then this square, I'm just going to go ahead and apply it. So that's going to be squared, that's squared, and then it's cosine squared. And then you can go through and you could factor out length of A squared, length of B squared, and you'd be left with 1 minus cosine squared theta. And then if we go through and use trig identity, the a minus cosine squared equal to sine squared. Now at this point, if you look at this, we've got the length of a cross b squared equals the length of a squared, length of b squared, sine squared theta. And so if we took the square root of both sides, we'd get a cross b equals a b sine theta. And that's the proof. And so you can see that the two definitions, as strange as this seems to look at them, they are equal. Okay, so just as with the dot product, there are a number of interesting properties for cross products. These are the properties that make the cross product useful. And these are the things that, the definitions that we go through and we're interested in when it comes to using the cross product. Like, why have the cross product? It's because of these properties. Okay, so the first and most important property is that A cross B is orthogonal to A and B. So if you go through and you calculate the cross product, the resulting vector is going to be orthogonal. It's going to be perpendicular. It's going to have a 90-degree angle with both A and B. So that's not obvious. So it's something that you'd want to go through and prove. That's an easy proof to go through and do, though. So if you have A is A1I plus A2J plus A3K. And you have B, and B is B1I plus B2J plus B3K. And you have A cross B. And here you could just use the definition rather than to write out the determinant. It's going to be I times A2B3 minus A3B2 minus J times A1B3 minus A3B1 plus K times A1B2 minus A2B1. And then if we want to go through and verify that that A cross B is orthogonal to A and B, here we can use our result from the dot product, and that gives us a test. So that's one of the more useful properties of the dot product, is that it enables you to test whether two vectors are orthogonal. If you take the dot product and the result is 0, then they are orthogonal. So what we can do is we can just go through and take the dot product between A and A cross B, and if they are orthogonal, we should get 0. And you could take the dot product between B and A cross B, and if you get 0, then they are also orthogonal. So let's go through and do that. So we have A dotted with A cross B. And if you go through and you do that, so when we take a dot product, we just multiply component-wise. So we're going to get this times this. And then this times this. Don't forget the negative here. So we're going to have minus A2. And then this times this. And then if we just go through and simplify this, we're going to have A1 times these two. So that's going to give us A1, A2, B3 minus A1, A3, B2. And this times this, we're going to have minus A1, A2, B3. This times this, we're going to have plus A2, A3, B1. This times this, we're going to have plus A1, A3, B2. This times this, we're going to have minus A2, A3, B1. And then if we check these, we should have some stuff cancel. So this is A1, A2, B3. This is negative. A1, A2, B3, so those cancel. We have negative A1, A3, B2, positive A1, A3, B2, so those two cancel. And then positive A2, A3, B1, negative A2, A3, B1, so those two cancel, and we get 0. So that goes through and shows A is orthogonal to A cross B. So we have proven one part of this. To go through and prove the other part, you could do the same thing with B. I'm going to skip that because it's redundant. It's basically the exact same proof. Okay. Now, when you go through and say that A and B are orthogonal to A cross B, one of the things that you do have to examine is the direction of A cross B relative to A and B. So let's just spend a minute on that. I'll show you what I mean. So if you have this picture here, right? So if this is A and this is B, okay, and A cross B is going to be orthogonal to both of them. The way that you can think about this is that A and B, you can think of them as forming a piece of paper, like a plane, a flat plane there, and then A cross B rises up off of the piece of paper. And it rises up at a 90-degree angle. So you have 90 degrees, 90 degrees, and then this is A cross B. If you have the reverse, where this is B, and this is A, and here is your plane that defines them, then the resulting vector points downward. And I probably could have found a better place to put B there. And then here's A cross B. And these are 90-degree angles. Okay, so the way that you keep track of this is called the right-hand rule. I can try and describe it to you, but I can't really draw a picture because I can't draw a hand very well. But the idea is if you take your hand and you have your fingers curl, your fingers represent A and B, and your fingers curl from A to B, then your thumb will point in the direction. Assuming you use your right hand, if you have your fingers curl from A to B, your thumb points in the direction of A cross B. Okay, so if your fingers are going to curl in the direction of from A to B, where A is the top vector, then your thumb would have to point downward. And if your fingers are going to curl from A to B and A is the bottom vector, then your thumb would point upward. So what I recommend that you do is go through and Google the right-hand rule, and you'll be able to find no end of pictures that illustrate that. But that's the idea, is that if A is the bottom vector, as in this picture, then A cross B points up. And if A is the top vector, as in this picture, then A cross B points downward. Okay, so that's something to memorize. Okay, so that is the main property of cross products is going through and finding vectors that are orthogonal to two given vectors. It's surprising how often that's something that you end up needing to do. Okay, so the second property. We have A cross B equals the 0 vector if and only if A and B are parallel. This is very similar to the dot product definition that we use for our test for orthogonal. So this is technically a test for going through and determining whether A and B are parallel. Do you need such a test? Not really. The easiest way to tell whether two vectors are parallel is just to look at their components and see if their components are in the same ratio, right? So if the components of one vector are all double the components of another, then they point in the same direction and one is twice as long as the other. So it's typically not difficult to tell whether two vectors are parallel just by going through and examining their components. But this is a fun proof because it's so similar to the one from the dot product. And the way that you go through and prove this, you'll recall the if and only if. That's where the implication goes both ways. So it means that we could translate this into if this is true, then this is true. And we could have if this is true, then that is true. So it points both directions. And so if you're going to go through and prove this, then you need to prove it both directions. And so we can do that. We can just start with let A cross B equal the 0 vector. So we're starting here on the left-hand side. Okay, well, if A cross B equals the 0 vector, then we know that the length of A cross B, if A cross B is the 0 vector, the length of the 0 vector is 0. So we could go through and say that the length of A cross B is 0. And then from there, we can use our first definition which is more theory-based. We have length A, length B, sine theta equals 0. And then again, we're assuming that neither A nor B is 0. If neither A nor B is 0, that means that these are positive quantities that we could go through and divide the other side, divide out. And so we'd end up with sine theta equals 0. And if sine theta equals 0, then theta equals 0. If theta equals 0, then it's saying that the angle between the two vectors is 0. So the vectors effectively are parallel. Vectors A and B. Okay, and so that's the proof one way, and then the proof the other way, you start over here, you say let, and this is similar to what we encountered with the dot product, and that is that the proof the other way is really just going to be starting here and going back up, right? So the proof one way, go down, the proof the other way, go back up. That's the same thing that we had with the dot product. So if we have A and B are parallel, then we have angle theta between A and B is 0. And then if angle theta is 0, then sine theta equals 0. Then length A, length B, sine theta equals 0. Then length of A cross B equals 0. Then A cross B equals the 0 vector, right? So if the length of A cross B is 0, and then that implies that the only vector that has a length of 0 is the 0 vector. So that means that A cross B has to equal 0. And that completes the proof, right? So we started on one end, worked our way to the other, and then we started on the other end, worked our way back. And that proves it both ways, which means that we have the if and only if or equivalence, right? So this is equivalent to that. Okay, so again, we rarely use that one, but it's just fun to go through and prove it. And then property 3, the length of A cross B is the area of the parallelogram where A and B are two of the sides. Okay, so it's helpful to go through and draw a picture for that. So if we have there's A, and here's B, then if A and B are two of the sides, that means we could form a parallelogram that parallelogram. And then what the property says is that the area of the parallelogram is A cross B, length of A cross B. Okay, so let's go through and prove that. All right, so if we're going to go through and prove that, to do so, you start off with the length of A cross B, and then we're going to go through and use definition 1. We can rewrite this into length of A, length of B, sine theta. And then we can split these apart. This is length A sine theta times length B. And then what is length A sine theta? Well, you'll recall from the first slide that length of A sine theta is the length of the vector that you, or the length of the distance that if you went through and dropped down a perpendicular here. All right, so if we went through and put a perpendicular line here, okay, where that is perpendicular to B, then this distance here is the length of A sine theta. Okay, well, so in terms of a parallelogram, this distance here is going to be the height of the parallelogram. So this is the height of the parallelogram. This distance here is the base of the parallelogram. So what we have is we have a product of the height of a parallelogram and the base of the parallelogram. And if you multiply base times height for a parallelogram, you get the area of the parallelogram. And that completes the proof. Okay, and that also completes the video. So that covers the cross product. Thank you for watching, and I'll see you next time.